I will start sharing that.
Great. Okay. Maybe let's start in a minute or so.
We used to use a different online board, I remember. We used to use a different board.
Yeah, it got bought by this company. So it's and they charge epsilon more. It's not too much more. So
anyway, maybe let's start. So we're very happy to have Dev Sinha, and he will be speaking today about geometric cochains and the phenotypics of homotopy theory.
Great, thank you. I'm gonna put a link to this board in the chat, and that way anybody who wants can kind of follow along. And then if there's something you want to look at back up, you know, just like we're in person, instead of looking to the left and seeing the other board, you can scroll yourself. Or if you want, you can scroll down and try to spoil the talk, but you know, spoiler alert. But thank you. It's been, I want to say, maybe since the past millennium that I spoke, quote unquote, at Purdue. Those were the days with, Jeff Smith and Jim McClure and Clarence Wilkerson, and it's wonderful to see how many that pretty much complete turnover from maybe my last audience, but a wonderful group. So I'm going to talk today about something that really could have been done in the 40s or maybe 50s if you wanted to give it a little time, but is just now happening, which is getting serious about submanifolds, or more generally, proper maps of a manifold to another as a way to define cochains. And I wanted to just start with some motivation. Really, for me, it starts pedagogically. You know, if you've got some space and you're defining chains, you can, and then eventually cycles, you can draw pictures, you can, it's a finite amount of data. If you think about singular cochains, what you're supposed to do is for every single map from a simplex in, you're supposed to give a number. Well, how do you do that? Well, there's a way to almost do it. Namely, if I take some submanifold W, which is the x-axis, then there's a cochain that I can define. Namely, take a chain and ask how many times it crosses that axis. What is the intersection number? And so, and it can be with signs. So this would be still 1, I guess, or we'll see, 1. So 2 would be the value of the cochain. And it's, this is a way over the integers to give a number, just like d theta does over the reals, right? Problem is, it is partially defined. You can't do this for, not lots of non-smooth things, and even not all smooth things. You need transversality, but it's there as an avenue now. It's always been something that people have done with tome classes, cohomology classes. Although those are hard to quote unquote piece together, because what you want is also the ability to maybe, not take the x-axis, maybe go out in some other direction for some reason. You have some reason that you want to piece together things with boundary in order to make these intersection cochains. Okay. Pedagogically, this makes some jobs easy. So for example, if you have a fiber bundle and you have one of these cochains, and the point is that here you've got, if it's codimension D, in other words, codimension is the dimension of E minus the dimension of W, then, and I've got my P, and this is like a fiber bundle with compact fiber, then I can just apply P to W, And this will be codimension D plus the dimension of the fiber, right? And that's the wrong way map. If I by abuse call the cohomology class associated to W just W, or maybe I'll do it this way, or maybe tau, sometimes I say tau W for like a tome class. So wrong way maps now, they have this, I don't know, when I studied them as a grad student, this mysterious shift in dimension, and then they're not always defined, but here clearly there's a good, reason that they exist. Namely, you're just composing, normally if I started with W to B, if I take the pre-image, that preserves codimension. If I take the pullback or pre-image, if W is a submanifold. But if I go the other direction, that's not always defined, but it is in some cases, and that's the wrong way map. And this kind of reasoning can help. Again, this is maybe more of a pedagogical thing. And if you've got a bunch of these maps, you want to understand properties of wrong way maps, basic functionality is, for example, immediate, then this kind of reasoning is very helpful. What are some other motivations? Maybe still at the more pedagogical level, we calculate the cohomology of rings of projective spaces as a way to know that CP2 isn't S2 wedge S4, for example. And there, if you have this philosophy of submanifolds, you realize that the cohomology classes are represented by linear subspaces of the projective spaces. And then the cut product is just basically reflecting the fact that the intersection of something codimension I and codimension J is something codimension I plus J in general with transversality, so almost always. So it's this basic linear algebra fact that's giving us this this ring structure that we then use pretty much. I mean, it almost sometimes feels like 99% of the cohomology rings we know in algebraic topology are somehow derived from the projective spaces. Here's one that isn't necessarily configuration spaces. If I take configurations of 3 points in R2, so I'm going to define a class alpha ij v as a cochain. It's going to be where, so this is the space of just collections of points 1, 2, 3. These are ordered, labeled. Okay. So alpha ij is going to be the submanifold where point I is, say, thinking about my picture to the left, well, is in direction v from point J. And if you think about that a second, that's a codimension 1. So this is going to be one of our geometric cochains in degree 1 of this configuration space, right? And these end up being the cohomology classes are the cohomology generators. And then and you can show that they're independent of V. So you have your favorite V, I have my favorite V. They're going to represent the same cohomology class. And then you have this relation that everybody knows, but maybe the proofs are a little, they're clever. But if I now think of, for example, points where I've got 1 and 2 are, so this is going to be again, I'm defining a submanifold of configurations of 3 points in R2, where 1 and 2 have the same Y coordinate, and point 3 is at that same level or above. This ends up being a manifold with boundary, and in this theory, then the actual the differential in the cochains is the same as just taking the boundary. And so the boundary of this is what I get when, well, point 3 could be down here to the left. And so if you look at it, it would be like alpha 3, 1 with, going to the right, or here, or sorry, alpha 3, 1, 3 is to the left of 1, and also alpha 1, 2, or here, alpha 1, 3, alpha 2, 3. So again, these are, so the other big point of this, sorry, I meant to say this coming into all of this, is that as, you know, the founders of topology envisioned, product is intersection. That's really, you know, the sum of things is union, and their product is intersection. And so if I have alpha 3, 1 means that 0.3 is to the left of 0.1, and alpha 1, 2 means 0.1 is to the left of 0.2, then their product is, if that's transverse, configurations where 3 is to the left of 1 is to the left of 2. Okay. And so if I look at the boundary, it comes in 3 different pieces. And that means that this product in cohomology is 0. That's the Arnold identity. So this gives both a sort of a geometric rationale, and by the way, it's giving you a witness, a cochain, a witness for the relation. And as algebraic topologists, that's one thing we're supposed to care about. Not only that things are equal, not only that some relation holds, but if they don't hold on the nose, here's some reason that relation holds, and that can maybe be useful data down the line. By the way, in the plane, if you allow yourself the real, or actually the complex numbers, if you allow yourself complex coefficients, this identity can be realized at the cochain level. It's a strong formality. But here is a sort of a more just explicit, and this works in any dimension, way to see that this relationship in cohomology holds. All right.
Dev,
Yes.
I have sort of a philosophical question.
Sure.
Why say cochains and cohomology at all, and not just work with chains and intersection products?
Because, well, so here's the, even in the R2 case, the cochain is the x-axis. That's not a homology object. That's a cohomology object.
But
So,
can you think of that as a chain?
if you want to do something with locally finite, and so you would have ordinary homology versus locally finite homology everywhere. But at that point, locally finite is a much longer preface than co. So
I see.
so why bother? And it's also, I don't know. I mean, philosophically, homology feels like maybe the more basic thing, and the cohomology is a measuring thing, right? And that's how I look at this here. If you look at this picture, this W, the x-axis is counting winding number, right? It's this measurement of the chain. Similarly here, if 0.1 goes around 0.2, that's the cycle, and this looking for 1, 2 to the right of 1 is a measurement of it. So to me, it's sort of naturally, it is using very much the same kind of objects. And obviously, if W to M is supposed to be proper and M is compact, then you do have the same set of objects, and that's Poincare duality. So this is Poincare duality at the chain cochain level, if you will. But yeah, they do feel different for those 2 reasons that I just said. Thank you.
Okay. Yeah.
Let's see. Let me just briefly say that I won't flesh this example out, but even in pure algebra, there are theorems that I've proven which use this kind of reasoning. By the way, if all you care about is things at the cohomology level, you won't need the things that I'm talking about today. I mean, it's just nice conceptually to have the picture. But as I said, once you even want to start piecing any of these together, tome classes of things without boundary won't won't do it. And once you start talking about products as well, you're often then it gets more complicated. So in the cohomology of a symmetric group ends up being the same as a cohomology of configurations of endpoints in R infinity modulo the symmetric group action. I won't sort of review why, but this is just something in algebra, or at least you can define it for your algebraic colleagues purely algebraically. This is a manifold. Well, if I cheat and put a capital in here and say the same degree, for any D there's an N, so that this isomorphism holds, and this is a manifold. And for example, an H3 class in configurations of 4 points looks something like this. I've got S1s. I'm going to parameterize this by a 3 manifold that's going to be a fiber product of S1 cross S1 over S1, and those 2 of those S1s are going to tell me where these antipodal, the really RP ones, what these little symmetric orbital things are doing, but they can turn independently. The third S1 tells me where that whole system is. And one thing we use is that H upper 3 is represented by the submanifold of configuration spaces. And again, this is, the left is homology, it's compact. The right is cohomology, it's proper. The submanifold were 4 points.
Are you working mod 2, or is it like a?
Yeah.
Okay.
Thank you. This is mod 2. There's similar stories at odd primes. The geometry is still, I don't know, I have some questions there, but the point is that these collinearities or sharing of coordinates end up being an expression of the full mod 2 cohomology rings of symmetric groups. In this case, these 2 pair because exactly once, these 2 pair non-trivially, exactly once in the 3-dimensional family that I told you about, do 4 points share their first coordinate. So, so even in sort of quote unquote pure algebra, you can look at these things. And something I'd love to explore sometimes is, configurations in Rn maps to configurations in any manifold. And so the cohomology restricts. So the question is, when does this class lift? You could actually say, well, maybe when the manifold has something like a codimension 1 foliation, that you can define it in this way by. So this might start to connect, and I haven't pursued that, but this might start to connect the cohomology of unordered configurations and manifolds with things like foliation theory. Okay. And then a good part of the motivation is a longer term project to actually break new ground in trying to understand homotopy types and homotopy classes of maps geometrically, but through smooth topology. So let me now give you some details. Any questions about those examples? Take a sip of coffee. Okay, so our objects, we want cochains, we want then manifolds with boundary that we can glue together, because maybe you can't always find the right manifold, but you can find 2 manifolds with boundary that match up to make one of these cohomology classes. Once you take manifolds with boundary, and if you care about product structures, which we do, I gave you some examples of ring structure calculations, you're in the world with manifolds with corners. So you have to think, think of the first quadrant or first octant, and you want that to be local. So that's straightforward enough. Note that you're already restricting your type of polytope significantly. The octahedron is not such a thing smoothly, right? Topologically, the octahedron is a ball, so of course we could impose such a structure on it, but the corners structure that we see is actually a non-example there. Already things like boundary are interesting. The boundary is no longer a subspace. So if I'm putting the definitions are there if you want to stare at them, but I'm going to talk through them here. So here's a subset of R2 that's a nice manifold with corners, right? You can even imagine this as an exact right angle. So this is, we have these strata. This interior here is what we're calling S0. This is S1, and S1 is all of those things. These are things with neighborhoods that are half spaces. And then finally, S2 is this point here. And then if you, and then what you have to say is a local boundary component is a choice of S1 intersect X for any neighborhood. So you're thinking arbitrarily small. So obviously, if I'm at this point X, there's only going to be one, S1, a neighborhood of that is going to hit S1 and just one connected component. Whereas in this Y point, I'm going to call this Y, any neighborhood of Y will have two components of S1 nearby. So these are the two local components. Near Y. And then the boundary is actually, I'm going to take not only points in S1, but also the data of local boundary components. And of course, the in the interior, there's no boundary in a sufficiently small neighborhood. So the boundary of this, let's call this teardrop T. The boundary of T is an interval which maps to T through a map which is 2 to 1 on the endpoints. So it's not a subspace. It's a map from a manifold. Okay. So all I've done so far is local. All I've done so far is the definition that, hopefully graduate students who we raise well would be able to come up with on their own, right? Maybe the stratum stuff is a little funny, but it's again, it makes sense. What people don't realize is the following example. So I'm going to take Sn, just think S2 cross quadrant, or maybe S3, and then I'm going to quotient by the action of the cyclic group of order 2 switching the two axes. So you've got a fixed point along here, but otherwise you're permuting, right? So this space, if I quotient fibers over RP2 or RPN with fiber the quadrant, and so it's a manifold with corners. So what is S1 of Q? Well, you won't be surprised. So S1 is going to be S2 cross over C2 with these two axes, right? Like the teardrop, the point. So by the way, it's always like into K to 1 and depth K, right? K factorial to 1, K factorial to 1 at depth K. So it's 2 to 1 here. So I've got two copies. And of course, that's just S2 cross 0 infinity if you want. So that's fine. But then the boundary of that, and so that's S1. So then the boundary of this manifold is S1, S2 cross 0 infinity. The boundary of that would be S2. So boundary squared is S2. So the boundary of a boundary is not 0. Is not empty. We're used to manifolds with boundary of boundary is empty. You might guess if you think about polytopes, you might guess that boundary of boundary would always come in these pairs which cancel. This is sort of a canceling pair through the antipodal action on S2. Because there's these two pre-images in boundary squared, you're always going to get an involution, but it's not, you know, it's not of the form manifold cross C2. In this case, there's a free involution on S2 or Sn, and it's non-trivial. It's, you know, so this is a key example. If you want to use manifolds with corners, you don't get boundary squared equals 0 for free, right? So this is one reason this wasn't worked out in the 40s or 50s, presumably. I can't really speak to them, but okay. So that's one key technical thing. The other technical thing is I think less surprising. You want to work with co-orientations. So I'm giving the formal definition here, but the key is that what you want is really, if you've got a submanifold, you want an orientation of a normal bundle. And what that the connection with this definition is, if I've got an orientation of the normal bundle and then a chosen orientation of the submanifold, I get an orientation of the whole manifold. So that's relating those two orientations through appending the orientation of the normal bundle. That generalizes, again, there's plenty of examples where you want not just submanifolds, but you want more arbitrary maps into a manifold. And all you want to do is choose a relation between, choose a homomorphism between the orientation bundle of your W and the pullback of the orientation bundle of M. So this means that, for example, RP2 inside of RP4 is co-oriented. Neither of them is oriented. Then the intuition is that, you know, when are you not oriented? Well, if there's a loop, if there's an element of your fundamental group, when you travel around, the orientation reverses. Well, if you've got a submanifold and over every loop that the orientation reverses in the submanifold, it also reverses in the ambient manifold, then that data is going to be co-oriented. And if you know, this is going to represent, well, it's an RP2 inside RP4, so it's codimension 2. Any RP2 is going to represent the codimension 2 cohomology of RP4 over the integers. So even though they're not both oriented, the key thing is co-oriented here. Okay. So let's get to the actual nitty-gritty definitions. We say something is trivial if there's an orientation reversing diffeomorphism of it that commutes with a reference map. So again, what we have is, for example, RW is a map from W into M. Ultimately, we will define cochains through this data, but with an important proviso down below. So if I can basically act by C2 that commutes with this reference map, then I'm going to be trivial. And the key thing is that boundary squareds are going to be trivial. Then we say it's small rank if it's less than full rank everywhere. In particular, if the dimension of W is greater than the dimension of M. And then it's degenerate if it has small rank and the boundary is the union of something trivial and something with small rank. The point is that, for example, in an interval mapping to R, projecting onto R, so let me give you the little example here. Here's an interval mapping to R. This is not degenerate because its boundary is, or actually it is degenerate because its boundary then has a co-orientation reversing diffeomorphism. But if I, sorry, I meant to prepare that example and I didn't. But the point is that even if something is small rank, its boundary might not be small rank. And those you want to allow, just the ones whose boundary continue to be small rank or are trivial, those are degenerate. And so these are going to be our two key things. Let's see. Trivial and degenerate. What we're going to do is then, let me skip down to the definition of geometric cochains. Are represented by maps from proper maps from manifolds, which are co-oriented. But we're going to then quotient by this Q. So what I mean by equivalent is in Q star. We're going to quotient by this Q. We're going to quotient by things that are either trivial or degenerate. Okay. So here's a pop quiz. If we were in class, like, why are we quotienting by the trivial ones? Anybody? You're going to be like a calculus class. Trivial ones were the ones with this this involution.
To get a chain complex.
Yep. Right. And degenerate is a way to get us the dimension axiom. And a question I still have, is this necessary? Could degenerate, could you get away with less? But you know, it's anyways, we were able to work with those. Lipinski, this is something that I should have said at the beginning. This is all worked out with Greg Friedman and Animal Medina. We initially had an application. I'll tell you about that in a moment. And then we realized that, wait, there wasn't a theory here that suited our needs, except it was started by Lipinski. So these definitions are pretty much Lipinski's, but he didn't work out very much. He did a little bit of more geometric homology. He was a gauge theorist, much more interested in these ideas in an infinite dimensional setting. So anyways, so that's why you need to quotient, and that seems simple enough, but now your cochains aren't manifolds with proper maps, they are equivalence classes of such. So that's what I was alluding to at the beginning. Your cochains are already equivalence classes, and then of course cohomology is going to be further equivalence. But this is the substantial technical issue, and there's, I don't think, any way around it. You know, especially if you want d squared equals 0, if you want to use corners, well, let's start at the beginning. If you want relations, you want boundary. If you want products, you're going to use corners. If you're going to do corners, the most natural theory that has transversality for products is not going to have d squared equals 0. So you're going to have to use equivalence classes in order to get there. So, c'est la vie. Not surprisingly, it's isomorphic to singular cohomology. We work out 2 proofs of this. There's a framework of Kreck and Sinha that sort of says if you've got a theory with the following properties in the smooth category, it's going to agree with singular cohomology. Again, this is for manifolds without boundary. So, you know, including like say infinite genus surfaces and things like that, but not, you know, but they're manifolds, so they're nicer. And the other thing you can do is, if your manifold is cubulated or triangulated or something like that, there's an intersection homomorphism. So namely, so here's my manifold M, and I'll do a cubulation. And then if I've got a submanifold, or again, a proper manifold W, if it's transverse to the cubulation, then I can define an I of W is a cochain, which in this case would have, I'm going to do mod 2, was going to have value 1 on these guys, and it's going to have value 0 everywhere else, unless somehow it intersects somewhere else. So I of W is just going to be the cochain. So I of W is going to be a cochain, classical cochain in the cubical setting on M. Okay, does that make sense? And we show that then inside of the geometric cochains of M, you've got the geometric cochains transverse to the cubulation. And that's mapping through this I, and both of these are quasi-isomorphisms. So that gives you, that's again this classical picture intersection again of proper with compact. W here, M could be again an infinite genus surface, W could be some curve that goes out indefinitely, that kind of thing.
Dev, and coefficients here work over any ring, right?
Yes, any ring. I was just giving the picture mod 2, but any ring. Yep. Okay. So the thing that actually in the end we almost thought was not true is that you can define a product on this gadget with these geometric cochains through intersection or fiber product more generally. So if I've got a W and a V, I can take the fiber product over M. If they're submanifolds, that's intersection, codimension adds. This is a pretty picture. And again, it inspired, it's why we call cut product, because it's dual intersection like this. Oops. But our cochains are equivalence classes. They're non-transverse representatives of any two such, and then, you know, of course, and many possible transverse intersections. And so, you know, is this product even well defined now that our cochains aren't just submanifolds or manifolds over the manifold in question? Is this product well defined? For a while, I thought about it and I said no. Thankfully, Greg Friedman figured out that you can you can get a well-defined product. So this is a case where it's nice to have persistent collaborators. And look, he just had to take any cochain and say we can decompose it into something essential, something inessential that we can ignore. He calls it trivially inessential, and then something inessential that we have to deal with. And that's where all the work is in checking that these products, and it also includes cat products, et cetera, are well defined. So I'll give you the just the option of going through that. I won't take time to.
So is this some kind of I mean, where's the content? Is it some kind of Sard's theorem or something like that? I mean, you do have to like approximate transversally or something at some point, right?
Well, so that's sort of a different, then you would want, I mean, the approximation transversely is like in this statement here, this statement 2, for example, that you need, so there's plenty of Sard's theorem kinds of statements there. This is more roll your sleeves up and say, well, my cochains are equivalence classes. You know, if I'm doing, say, the projective spaces or configuration space example, I've got the thing I care about, which is another projective space or this linear subspace. But the way we've set up the definition, I could also have an involution on something, just an extra piece in the equivalence class, right? And so, or I could have something which is small rank. And then you have to go through and intersect those, take those pullbacks and check, and some of them are easy. If I have an involution and I'm pulling back, I can get an involution on the pullback, etc. But some of those are hard. Going through all that, and I would say to answer your question, it's this definition, realizing that you could suss out the ambiguity in your cochain in this way that the definition didn't quite give immediately, but breaking it out into this trivially inessential versus non-trivially inessential. So by giving you this definition, I'm giving you a strong hint. From there, there's still a lot of work to do, but it's checking well-definedness through the definitions of what we're setting to zero.
Can I ask one question before you got out of this? So I've seen this picture before, because anybody would, if you scroll back down, or up, whatever. Sorry. If you look at this W, that's going through your accumulation, right? But if I start moving it, then it can be it can intersect the corners of your accumulation, and then it starts changing sign. So you have somehow this it's not quite a wall, but a corner crossing phenomenon.
Yes.
And doesn't that give you any trouble? I mean, usually that kills everything.
Well, that's this quasi-isomorphism. You're not allowing those in here, and you're saying that the full cochain algebra, I can get, this being a quasi-isomorphism would mean that, for example, one way you can prove it is give a homotopy. So you take your corner one, and I'll just make an arbitrary choice of something epsilon close, where it's moved off the corner. And then you'd have to sort of, you've got boundaries, you've got a whole chain complex, but you could imagine going through codimension by codimension and just choosing something that's homotopic, that's good, right? So this is the sort of, as Manuel says, this is where Sard's theorem, etc., comes in, that you can take the whole thing where I is not defined, and it's, and this shouldn't be that surprising that you get the same answer. What is a quasi-isomorphism? We're getting the same answer on cohomology. So any cohomology class in M is represented by such a W that intersects the cubulation well. That shouldn't surprise you, right?
Yeah, but if you're carrying around all these choices and you're making intersections, I think that's hard to track.
I mean, so you're probably, I don't know who's speaking, but you're probably so much of a infinity person. This is just a pi naught statement. This is just saying I can move any cohomology class into good position.
At the cohomology level, yeah.
Yeah, at the cohomology level. That's what this quasi-isomorphism is.
But
then if you wanted to keep all those choices, that would be another question. Let's hold that for for some later thoughts, because I want to touch on. That's a good idea. You're right that looking at some of this and thinking about all the ways that you could make it transverse, that's a much more subtle structure, and that's a structure that excites me a lot, right? But this statement is just a sort of a pi zero statement rather than a. Does that make sense?
Yeah, sort of. All right, thanks.
Yeah, sure. So yeah, so we have our C gamma. Oops, sorry, C gamma of M, whose homology is the cohomology of M, and we also have, singular or cubical, whatever, cochains. And now this one is commutative on the nose, but partially defined. And this one is non-commutative, but in fact E infinity, and of course fully defined. And so these are two different approaches now to cohomology, one which is has been much better developed. one question is, how do these compare, right? And they can't be equal because the non-commutativity is where Steenrod operations arise. So let me show you that through the intersection homomorphism. So here, I of W is going to be 1 here and 1 here and 0 here and 0 here, whereas I of V is going to be 1 here and 1 here. And then if I do I of W cup I of V, in the cubical setting, it's front face, back face. So in fact, let me highlight them in green. This 1 followed by this 1. This is 1 when I evaluated on the whole square. So I of V cup I of W is 1, whereas W intersect V is empty. So its value on the square will be 0. So here's a little example that shows you this direct comparison map is not agreeing. Well, what we do with Annabelle and Greg, Annabelle is the one who realized that any cubulated manifold, there's a beautiful vector field. Actually, some other folks, I know my colleague Robert Lipschitz and some gauge theorists have used this as well. There's a beautiful, pretty much a beautiful vector field where you take a way to flow from 0 to 1, and you can then take the product vector field on any cube. So we use the standard logistic map, so we call this the logistic vector field. Then you take the product is now a way to flow from the initial corner to the end corner. And what we show is that while V and W, their intersection doesn't reflect it, if I allow W to flow sufficiently long, then eventually its intersection properties are going to reflect the cubical, the combinatorial cup product. So what we do, if you like to be symmetric, we'll flow W forward, that's this Ft of V, and we'll flow V backwards, and that's F minus T of V. And then after the flow, intersection looks like a homomorphism. Okay? So this is comparing them with now the smooth topology, allowing a comparison. Okay. Interestingly, we found similar use of vector fields on cubulated, triangulated manifolds in the mathematical physics literature. And so it would be interesting to, although theirs are discontinuous, be interesting to start playing with the more the on a smooth ones. I mean, this is sort of this lovely smooth object that's living through this combinatorial structure. So we hope to play with some of those ideas down the line. What I wanted to do now, and please let me know, do I have 1 minute or 6 or 11?
Take 11.
Okay. 11 should be plenty then. I don't think I'll need that, but it is sort of get to these the next steps, hopefully. So we used vector fields to compare the intersection product, the fiber product, the smooth topology product with the more combinatorial product from the cubulation. But you can also use it just to resolve this fact that that our product is only partially defined. In particular, so let's recall we need W transverse to V for a product. This always fails for W, right? So that's an issue. It's a point to keep in mind. It's kind of hard to have nice models for things if you can't take x squared, right? You can't take a single class and multiply by itself in this theory. that's an issue potentially. Of course, you could then, what you want to do is be able to move it off. If you think about moving W off of W, one way to do that would be a vector field, right? So, so if I take W and I have some sort of vector field, and it can vanish somewhere, including on W, and then I can just take the flow of W, then in some cases, W times FTW is going to be a transverse, and that's going to be the product, right? But of course, that's choosing a vector field, so dependent on a vector field and some sort of time for flow, but there's at least a potentially canonical time for that. You can take the limit as t goes to 0, right? And what that would be is in the product W sort of intersect W infinitesimally is going to be places where the vector field, in this case, is where the vector field vanishes, but more generally, it's the submanifold of W. And again, there's transversality everywhere here needed, such that this the vector in the vector field is contained in the tangent space of W. So you're trying to move W off itself, but you end up just moving it somewhere else on W. So that would be a way to just take a vector field, and now we could define what W times W is. Again, not everywhere, right? Because given a vector field, there are going to be some submanifolds for where this is not a good thing, but we've got a wider area, and it's kind of an interesting idea that we can then take. We can take further. So alternatively, we could flow backwards, or I could have just said V and minus V with the same T. We could flow forwards and backwards and take that, and that's nice and symmetric. So, well, this was one choice given a vector field. Once we make one choice, now let's take the idea of you can have all these ways to move things off themselves, right? So, let me do the next example. If I have two vector fields, and of course, I wanted the first vector field to be non-zero, right? I want these to be almost everywhere independent or something like that. Again, this is all sort of a conjectural picture anyway, so I don't have, there's no theorems here, so I don't have precise conditions. Then if I have any x in R2, I can get a vector field on M by taking, you know, if x is, say, a times basis vector plus b times second basis vector, then I'm just going to take a times v1 plus b times v2, right? So now, it, you know, then what we're going to do is we're going to take a union over x comma minus x in S1, so really RP1 of, you know, f minus x1 w intersect fx1 w. So I'm moving w off of itself now in a one-dimensional family. So here's W, but I bump itself off plus and minus direction. And I'm going to do that in all possible ways. And of course, the plus and the minus exchange. So that's really indicating them over RP1. And I'm taking that one-dimensional intersection. And of course, I could do this with a number of vector fields. And move W off itself in all those ways. And then the conjecture is that this object is exactly representing square D, which is the degree of W, minus N on W, on the class represented by W. So this is giving us a new way to represent Steiner operations. It's saying that they're arising from sort of resolving the difficulty of multiplying something by itself. Once you start doing that by bumping something off, well, let's just bump yourself off in all possible ways. More than that, if we take I'm going to take and again, this now will basically only make sense to folks who already know about E-infinity structures and disks operads and compactification. So there's a lot to get here. My apologies for those who aren't with me at this point. But if I take, an X1, XK in configurations of K points in RD, and then a W1, WK, then I could map it to, I'm going to flow according to X1, W1, intersect flow according to X2, W2. And I'm going to take those fiber products. And that's a way to now parameterize multiplications through configurations. So this looks like something like an operad action. As written, this has no chance of extending to an operad action because there's not a really good composition here. So the conjecture is you can take the limits as t goes to 0, because maybe I have a t here. Take the limits as t goes to 0, maybe use the Fulton-McPherson and maybe sort of let me write it out. Take the limit as t goes to 0, use Fulton-McPherson modulo translation and scaling operad, and get a partially defined E-infinity structure on these geometric cochains, which then compares to as E-infinity algebras. So this is just a new perspective. For those who don't know, the E-infinity structure on the cochains, which is this remarkably rich but highly non-trivial combinatorial study structure on cochains, it encodes the homotopy type. The conjecture is that you can also encode the homotopy type through smooth data. That's it's really conjecture that I was advertising in the talk then. And it's sort of through manifolds and flows and intersections and tangent bundle data. All of those things can package together to tell you about the E-infinity structure on cochains, and thus the homotopy theory of any manifold. That would be wonderful. look, partially defined E-infinity algebras, there's a lot of work. There's some existing work on those, but there even be some categorical work, as well as the geometric work, that these are defined enough. Again, these aren't all deformations, but this is using a bunch of vector fields to give some coherent deformations of the product structure. The takeaway again is not that classical E-infinity is resolving non-commutativity. That's a problem. This E-infinity structure would be resolving partial definedness, but it would still be partially defined. It's a kind of a funny thing, but there it is, and I'm going to stop.
Thank you. Are there any questions or comments?
Oh, yes. May I ask you, do you know if your geometric cochains are partially defined algebra, in the sense that the composables are quasi-isomorphic to the tensor product of the copies of the cochains?
Yeah. We haven't checked that. So the statement partially defined is in a very weak sense. In other words, there's a product, it's associative, it's commutative, etc., where it's defined, but we haven't. It's certainly true, but we haven't written that one down.
Okay, thank you, Dev.
Sure.
So Div, so you're encoding the homotopy type using smooth data, I get, or that's the goal.
Yeah.
But there's, I mean, since you're in a manifold, you can try to remember more at the chain level, right? So, you know, like any space has this diagonal map, and sometimes you can approximate that diagonal at the chain level.
Sure.
So, I mean, the cup product is defined for any space, right? And then you can try to combine the intersection structure on top of this, right? So, I mean, have you thought of trying to express this structure using geometric chains or cochains? For instance, I would like to see something like something that's a E-infinity algebra and simultaneously an E-infinity coalgebra, and these structures should be compatible in some Frobenius sense, and that's kind of my dream, you know.
That that seems, I've had the same dream, but I'm not terribly optimistic. Like somehow, what's a similar yeah. So here's how I would reflect on what you just said. On geometric chains, you have this, you know, canonical, although partially defined, technically difficult, because again, we're working with equivalence classes product, right?
Right.
W intersect V. What about the coproduct? Can you delta W on the homology side? What should that look like? To me, it feels like, I don't know. I have no ideas how to get at a coproduct without some sort of ambient simplicial or cubical structure.
Right. So that's what I was thinking. I was wondering if you can work with like triangulation or cubulation of W, and somehow like get an induced triangulation on the intersections, but that sounds hard, right?
Right. So not on the ambient manifold M, but on the W representative.
Right. Just like geometric simplicial chains, you know?
Yeah.
Like.
Yeah, that's a nice idea, actually. I hadn't thought of that. So if W comes triangulated, you could do the first face, last face thing,
right,
thing there, and that would probably do it.
The issue is how to put a natural triangulation on the fiber product or intersection, right?
Yeah.
Then that would involve a choice, and then you have to keep track of, I don't know.
Yeah, I mean, what you might need is something even more flexible than a triangulation or cubulation, although then,
Right.
yeah, I don't know. Yeah, no, I think that's quite, I certainly applaud your dream. And as much as I'm optimistic enough to sort of say, here's how we could maybe do an E infinity structure, and there's so much technical work to be done on this side. I don't feel like I have any ideas for how to get the co-product as nicely as the product works in this theory.
Right.
Yeah.
The co-product seems to be something more combinatorial, like an approximation of the diagonal map,
Yeah.
right? It's
Yeah. Yeah, I agree, and that seems to be, yeah.
So I was also going to suggest some references that come to mind. You might be aware of these. You know, Jim McClure, I wish he was here, but he has this partially defined intersection structure.
Yeah.
You probably know that. And also maybe which is not as well known to us algebraic topologists, Fukaya and the symplectic topologists have some way of dealing with these transversality issues, which is very interesting. Like they think of chains as a pair of a chain and a cochain. And they think of that as the cap product, but they carry these separately.
Yeah.
And then they're able to construct fiber products using this model and so on. And that might be interesting. Yeah, I think maybe Joyce uses a similar approach. Yeah.
We would certainly need to get the right, you know, and there's both. I think May Krish also have partially defined algebras, as well as McClure, as well as there's a couple references out there. We haven't gotten far enough. We really haven't taken any steps towards this story, other than sort of envisioning that this is how you could have something like an E infinity. You could have any partially defined E infinity multiplication. So yeah, and I also sort of, I hadn't thought about trying to use this as a technical tool, but yeah, I think of the main objects here are the geometric chains, the geometric cochains, and the pairing between them. And then, you know, and then singular maps to both the geometric chains and the geometric cochains. Well, geometric chains map to geometric cochains, right? So it's, yeah, but I do think of that pairing between those as sort of the central story. And then the intersection map is an adjoint to that, essentially, etc. But again, so I would be interested in, if to pursue this and extend it in a more serious way as needed for further applications, would want to understand sort of, okay, partially defined pairings between, you know, algebras, coalgebras, and things like that. That's
right.
Getting it all settled. Probably want somebody who's fluent in infinity categories on the team.
Right. Are there any other questions or comments?
I'm not very infinity categorical minded, but I wondered whether you've seen the work of a Spivak on derived smooth manifolds.
Yeah.
Yeah.
David was a postdoc at Oregon, so
Okay.
But yeah, I don't know. Right. So then it's sort of, I thought about it a little bit, but yeah, quick answer. I don't know how, if expanding that, certainly expanding that should give you a fully defined algebra. Somewhere things have to break down though, because if you had a fully defined algebra that was commutative, modeling cohomology, then it would extend to an E-infinity algebra trivially, and that would seem to imply that Steenrod operations are all trivial, and we could all go home because math doesn't work. So
Maybe that's over the rationals or not. This is maybe it's over the rationals that work. I don't know.
I mean, David's work, I think it's over the integers. I think you've expanded your notion of manifold so that everybody's transverse. So you always get pullbacks, as far as I understand it. Yeah, I'm not sure what breaks. I mean, one thing is I don't think he did with corners necessarily. Maybe, I don't know, maybe, now that we've done all this, I haven't thought about that question in a while. Now that we have all the technicalities, I realize that, gosh, well, if you now have one of these objects with corners, can you even quotient by what you need to have boundary squared equals 0? Maybe you can't even really get a chain complex with those objects. I don't know.
I see.
So worth thinking about, but again, there's you obviously can't prove anything too strong because now you're fully defined. If you had an E-infinity thing equivalent to singular cochains, you'd be showing that homotopy theory is trivial.
Very good.
I sent a reference here for these Fukaya style Durham chains. This was a student of Fukaya that used these to construct string topology operations, but there's a nice section, a nice exposition of what these Durham chains are and what they can do. Yeah.
Cool. Thank you.
There's no corners there. Yeah, actually your domains are open sets in Euclidean space. And then you have a form as part of the data, a form in that domain.
But is this then over the reals?
Over the reals, yes. This does, yeah, exactly. This is very much over characteristic 0.
Yeah. Yep.
Yeah.
I mean, and again, I'm sure there's lots of great applications, especially if you want to do things like loop spaces or infinite dimensional. But I kind of the interest here is, can I didn't say at the beginning, can we get some theory that lets you do mod 2 calculations or mod 50 whatever 53 versus over those coefficients, like we can use Durham over the reals. So that was the idea.
Right. Yeah. Anyway, this was great. This is hard stuff. I'm always like scared of this.
Yeah, it ended up being harder than we thought to get the foundations down, but it's nice. There's a lot of the other thing to say is that I gave the example of push forward maps, but pretty much sort of any kind of intermediate topology, characteristic classes, all the things with sort of Chohm spaces, loop spaces are fun to think about. Again, we'd need to do some work to do that, but the bar construction becomes, the basic thing is whether my loop passes through a submanifold. That would be sort of bar W, but then you could ask, does the loop pass through W and then V? That's what W bar V is in the bar construction. So this gives you a sort of a way to kind of conceptually understand a lot of topology, pre-1970, say, everything people did. You can sort of see what's going on, so to speak, in this theory, but we haven't really developed that. That's just intuition at this point.
Okay. Any other questions or comments?
Probably this is unrelated, but this is sort of like a, perturbing things. I don't know, you're talking about configurations, so I'll just like throw it out. But well, let's say you have, configuration space of points in a manifold, and you want to and let's say it's a compact manifold, and you want to add a point somewhere.
Yeah.
Well, you can't do that, but you can like if you take chains with coefficients in Z mod 2. Or if you want to add like P points in your favorite ball, you can do it with coefficients in where you take like chains with coefficients Z mod P. And sort of like if you've, I don't know, if you've configurations of points and sort of like the broader bracket vanishes, then at the chain level you can sort of pretend they're invisible and they pass through each other. I don't know. I don't know if I mean this stuff isn't really related to like what you're trying to do, but just sort of, I don't know.
Yeah, I mean, there's a few different ways that I see sort of configurations. Well, as you saw, one of the main conjecture is that you can then use configurations to flow these W's. The other thing is that as I just alluded to, this kind of very much the Fred Cohen almost school of configurations and mapping spaces being basically the same thing. In this dictionary, if I've got the space of maps from M to N, and I've got a good, here's a definition that we don't make, but that's in my mind, called a Poincare system of N is a bunch of geometric cochain representatives, is like is a geometric cochain model for the cochains that's discrete. So think about in the torus, think about the two longitude meridian, the point that intersect, that's sort of modeling the cochains on the torus and the whole torus itself. Then what you can do is take the pre-images of, well, then take points in M with labels in, so configurations sort of in M with labels in the submanifolds in N. Those are going to define chains by just saying, okay, this point is going to go to that submanifold. This point goes to that submanifold. And then you could ask, okay, the point, when the points come together on M, they intersect. I'm going to intersect the things in N. So that to me is sort of this, what, you know, configurations with labels, why they come up all the time in maps, that those are essentially the homological or cohomological models for mapping spaces, because I'm keeping track of which points in M and N go to which places. Maybe I need to actually take submanifolds in M going to submanifolds in N or something like that. So anyways, this and then configuration spaces become like, okay, maps to spheres or maps to loop spaces or things like that. So I think, you know, Fred Cohen made a lot of hay out of this in a way which, if you sort of look paper by paper, feels ad hoc, but you sort of realize that some of these, I mean, there's often like collapse maps or these kinds of things. But, you know, again, if I had infinite time, I would love to sort of refound some of that in geometric cochain theory to say, okay, this is what's going on essentially, right? This is iterated loop space theory. We're looking at maps from a sphere into N, and we're then taking these submanifolds and going to just keep track of which points go to which submanifolds and think about those coming together. Maybe the points in the sphere I need to use something like Fox-Neuwirth chains to really get a cellular kind of model, and then this might be some cellular model for the mapping space or things like that. So there's this deep connection that again Fred made a career out of, that you know, now there's a lot more people. At the time there were a lot of people who thought about mapping spaces, and then Fred was almost unique in how much he valued configuration spaces. You know, whatever, 30, 40 years on, lots of people think about configuration spaces, not as many people think about mapping spaces, but I feel like that bridge could use some more travel, as Fred showed us.
Okay. There are no more questions. Let's thank Deb again. thank you for this nice talk. And
Thanks.
I'll try to send you an email. I have many thoughts on this. So
Yeah, and
yeah. Of course, I'm interested in this non-simply connected case, and in
Yeah,
that
yeah,
case, you
I
do need coalgebras and work with chains, because if you dualize, you lose the information of the fundamental group. You only
Yeah.
remember this Malsev completion.
Yeah, and actually, and Nir and Ben and I are going to be meeting in 40 minutes, and one day maybe we can report our progress. We're also working on the non-simply connected case, exactly the Malsev.
Right. I heard from Nir. Yeah.
Yeah.
A
So
few months ago. Yeah.
Yep.
Great.
Yep. Maybe eventually one of us could report on that. Still
Yeah.
have things to prove. So
Great. Yeah. Okay. Thank you so much, Dev. Good to see you. Yeah.
take care.
Thank you.